We'll go ahead and graph them. 1.5 is up at 1, 2, 3, 4.7. Negative 1, 0. 0.5. 0 again. And we're off the page. So connecting those dots kind of in the order that we have, we want to just try to get this a smooth curve. Seems to go down and then back up here. Now, I'm not really sure if this goes down again and gives me another 0, but it kind of looks like that's what it's doing. But we still at least get a good idea, a general idea of what the shape of that graph should be based on just these points. If we wanted to be more exact in this area, we could try more decimals like 1.6, 1.7 and see what's happening here, or maybe 1.4, 1.3. But that'll give us a general idea. Now, one thing that we can do here, like if I only had 0.5 and 0.1, I know that I have to cross 0 here because this is a negative number and this is a positive number. Now, I do have that appearing here in the graph. But like over here, I'm not sure if it is or not. But if I could find that I have a negative value around here, then I could prove that there must be a 0 here. Because what's happening, anytime that I have a negative value here and a positive value here, I have to cross 0 to get there. I might not be able to find exactly what that x is very easily, but I do know that between here, since I'm going from negative to positive, there has to be a 0 in there. And so this location principle is useful to us because we don't have to be exact. We can kind of zoom in on it. With this way, like we're just saying that we don't skip numbers. It has to be a continuous function with all polynomials. Okay, so like looking at this one, they've got a table here. And just looking at this table, we can see that we're changing from a negative y to a positive y. And because we have that change in sign, we have to cross 0 somewhere. So somewhere between 0 and negative 1, those are my x's, I have to have a 0 in there. I don't have to find it. I can just say somewhere, I have a 0 somewhere between x's, negative 1 and 0. And then again, it's happening here between positive 1 and 2. I'm moving from positive 1 here to a negative 4 here. I have to cross a 0 somewhere between x's 1 and x's 2. Again, down here, it's changing from negative to positive, so I have to be crossing a 0 somewhere between 4 and 5. So it helps us to locate the zeros without really finding exactly where they are. Okay, now next we'll talk about relative maximum or relative minimum. And what these are contrasting, when we talk about an absolute maximum, we're talking about the highest value for the entire function. The problem is this function keeps going up forever, so there is no absolute maximum. We can always find another value higher than that. Or on this side, we can always find another value lower than that because we're going to keep going down forever. But we do have what are called relative maximum and relative minimum. Like if I zoom in on this area, everything around this point is lower than that point. And so we call it a relative maximum. Or looking at this point, everything around that point is higher. And so that's a relative minimum. And we can also call those turning points. And these points are going to be useful for just a lot of different kinds of problems. And the most number, like whatever our degree is, like if I have a degree of 4, then the most number of turning points I could have would be 3. Or here, this is probably a cubic function. Notice that there's exactly 2 places where it turns. Or when we had x squared, our graph was a parabola. Notice it turns at exactly 1 point. If I just have x, that would be like a power of 1. It's a line. It doesn't turn at all. It's always just a linear. It's a line. It's going up on one side, down on the other side. There's no turning point. So we always subtract 1 to find out how many turning points it has. Okay, so like for this one, if it's x cubed, the most number of turning points I could have would be 2. Notice that's what we have when we graph it. And what we can look at, well, first of all, we had the zeros before. We have a sign change here from negative to positive, and so we have a 0 in there. Notice this one only has 1, 0 because it doesn't go down far enough. Okay, now we can see here I'm going up from 1 to 5, it goes up, but then I'm going down again. So that's how we know that there's a relative maximum somewhere around there. Now, this one's identifying it as exactly 0, but we don't necessarily know that it's exactly at 0. Like I might go up to 7 before this or after that, but I just know that if this is 1 and 3, that this 5 is higher than those, so we're going up and then we're going down, so there has to be a relative maximum somewhere between that 1 and 3, or somewhere between -1 and 1. On the other hand, here we're going down 3 to 1, and then we're going up 1 to 5. And so somewhere in there, there's going to be a relative maximum, which we can see right there. Okay, so again, we come back to 0. We know that there's a 0 between -2 and 1 because of this sign change. We can see that x equals 0 is greater than the surrounding points. Now, they haven't actually zoomed in and found exactly that is, but it's okay to go ahead and just round that for now and say, well, that's probably a maximum there. If you wanted to know for sure, you'd have to choose points that are a lot closer to that to see if it really is. And then the same thing with this one. They're saying it's a minimum because it's lower than the surrounding points. Now, one thing that we can look at then for our table, since we know there's a cubic function, we know there's only 2 turning points, we've just found the 2 turning points, 1, 2, maximum and a minimum. And so I know that everything after this is going to go up. I'm not going to have any more up and downs anywhere, so I don't have to keep my table going in either direction. I know that this is enough to get a good idea, and it's always going to go up after that. It's always going to go down before that. And then I'm also sure I found all of my zeros because it's always going to keep going down, always going to keep going up. Okay, a word problem here. Basically, whatever the problem's saying, they've given us a function, so plug in values. Now, in this case, they started at 0 because we're talking about time. It doesn't make sense to start from a negative time. And we want to go to 1960 to 2000, so years since 1960, so we're just counting in 40. So we don't want to go much more than 40 on our graph, but maybe they go up to 50 because we want to go a little bit further to estimate what keeps going. But we'll keep graphing those so we get an idea what goes on beyond that. So we plot each point, connect it with a smooth curve. Now the second part of this asks to describe the turning points of the graph and its end behavior. So the turning points are our maximum and our minimum here. This is happening at about, I don't know, 17 or 18, and this is happening about 32 or 33, somewhere in there. Okay, so so we're looking then, we're adding those years to 1965, and so we get somewhere between there. For the end behavior then, we're just looking at what it's doing really on this side because this is just a starting point. We're starting here. This is really the end behavior that we're looking at. It's going to keep growing. Now, if we think about what trends in fuel consumption does the graph suggest? So it looks like between I think this was about 1966 or 67 up until, what did we say, about 1997, 1998, that the amount of fuel consumption was going down. But after that, people were using more and more, and it keeps growing after that. So that's what we're looking at for fuel consumption, is rising and continues to rise. Now, it asks, does it make sense for this to keep going forever? Like we see in our graph that it's just shooting up and it's going to keep going up. Now, this function may be good for what's happening between 1960 and 1990, maybe even to 2000, but it doesn't make sense as a long-term thing because eventually there's only going to be so much fuel available. It can't keep going up indefinitely. There's got to be other limits eventually that are placed on this. Here's your homework. If you have any questions, post them on Edmodo. I'll try to get back to you as soon as I can.